All right, well, then let's go to our speaker of today, Gary Steele. He's Antoni van Leeuwenhoek Professor in the Quantum Nanoscience Department, Canadian originally, but already for a long time in the Netherlands. He has a PhD from MIT, and afterwards he came as a postdoctoral researcher to Delft in the group of Leo Kouwenhoven. And afterwards he started his own group at QN. So, Gary, the floor is yours.
Okay, great. Thanks, Reike. It's great that we have that I have an opportunity to present a little bit about what we do here, and also that we as QN are now have the opportunity also to become involved in Quantum Delft. I think it's a very nice initiative. So I'm going to hopefully share screen, see if technology works. Technology works sometimes. Good. So is it okay, Dan? You see everything good? Okay, so so I'm going to tell you today a little bit about work in my group that is related to, well, my cover slide here shows you about what we do in our group. So the group is normally called Quantum Circuits and Mechanics, and I'll tell you today about topics that we use these things for quantum sensing and quantum simulation. So my name is Gary Steele, as Freek said. I'm part of the Quantum Nanoscience Department, and of course I am happy to receive funding from some of the nice people that want to give it to me. So first I'll tell a little bit of our department. So I'm part of the Quantum Nanoscience Department. We are sort of, you can kind of think of QTech as sort of a spin-off of us, technically. So we are a department of about 14 PIs working on topics in quantum nanoscience with three foci on quantum matter, quantum sensing, and quantum transduction. Also, maybe it's good to say, since this is also a public video, we are hiring a tenure track and senior level. And so if you are interested in any of these topics or know somebody who might be, please feel free to contact us via our department webpage. You can find the advertising, but if you want, you can also contact me personally for more informal information. So I want to also tell you a little bit about my group. So this is sort of a sketch of all the stuff that is going on in the group these days. Let's say the group has a core focus on something I call superconducting quantum circuits. And those are circuits that we make on a chip made of inductors, capacitors, Josephson junctions in a clean room, and made out of superconducting metals. And these behave actually, well, you can make them behave in a quantum way. So there are two main directions we pursue with these devices. One is what I'll call mechanics, and this is where we started in this field, and that's where we try to couple gigahertz microwave circuits made out of superconductors to mechanical objects, with the aim of eventually using these circuits to gain control over the quantum state of vibrating or mechanically moving objects. And if we can do that, we can start to do things like take advantage of the high quality factor of mechanical objects as a quantum resource, but also we can look to really crazy things like try to explore things like quantum gravity. On the other side of this drawing, we have is our work in what I'll call circuit QED. So we play around, I like to call it a bit, in circuit QED. And in this field, actually, we're not so interested per se in making a gate-based quantum computer, but instead at engineering quantum optics and quantum physics at microwave frequencies by combining inductors, capacitors, and Josephson junctions on a chip. So if you walked into my lab, you will see this. You'll see lots of these things. So this is to give you a feel for what we work on. This is actually from the people that gave the last Quantum Delft seminar. And these are dilution refrigerators, because to make these devices behave in a quantum way, we have to cool them down to very low temperatures, down to 10 millikelvin, to remove thermal excitations from the devices. And actually, this fridge here is a special collaboration that I have with Blue Force as part of my ERC, where we developed the now very popular helium battery as an experimental project, a research project together with the company. So some examples of the types of devices that we work with. So on the sort of the quantum circuits side, I'll actually talk about both of these in some level of detail today. These show some recent work we've done with quantum radio frequency circuits. We've looked at tunable couplers, where we can use Josephson junctions and capacitors to engineer different types of couplings between qubits. This shows here the devices that we have worked on to try to look at very large, heavy objects in quantum superpositions. And this is a millimeter, sort of a macroscopic millimeter-sized membrane. We found that these can have extremely high quality factors up to 120 million, that's low temperatures. And the last thing on this little highlight side is this recent result of SQUID mechanics. This is where we use a superconducting quantum interference device to read out the position of this little beam that can vibrate up and down. And I'll tell you a little bit more about that during the talk. So, but before we get into the details of what we do, I want to give also a little bit of a background about quantum sensing itself. So the title of my talk is Quantum Sensing and Quantum Simulation. And so I want to try to motivate a little bit, at least from my perspective, what quantum sensing is and why I would want it. So, it's a good question. What is quantum sensing? And it's sort of a simple working definition is that quantum sensing is whenever you sense, sorry, the zoom window is going all over the place here. The quantum sensing is in some sense, by some people defined as some sensing with something quantum. You have something quantum and you sense with it, and that's quantum sensing. Then of course, if you want to say I'm sensing with something quantum, you can also have a discussion about what is quantum. And then maybe people start to diverge about their personal opinions. Most people will definitely say that atoms are quantum. People would probably say that photons are quantum. Some people may say that light is quantum. Some people may disagree with that concept. And then, although I believe myself, I am personally also quantum, probably people would not consider me to be a quantum sensor. So aside from these pedantic, possibly semantic discussions about whether something is quantum or not, I think an even better question to ask in this context is quantum useful for sensing? And in particular, could quantum somehow be better than classical for sensing? That's sort of the implication in the title would be that if I'm going to do quantum sensing, it's going to be better than classical sensing. And that's an interesting question, and I want to sort of give my own personal insight of working in the field of optomechanics for a while into the answer for that. In a sort of very simple way, you can think about it like this. What happens? What's the difference between classical and quantum? So I'm going to consider a simple case of just a particle who's going to move in only in one dimension. In that sense, in that case, there's only two degrees of freedom: the particle's position and momentum. And we know that in classical mechanics, you can represent this on this phase-based plot, which is a plot of position and momentum. And in classical mechanics, this particle can have a position and a momentum, period. And that means that the particle's state is an infinitely sharp point in its plane. Now, what we also know from quantum mechanics is that if I do in quantum mechanics, this is different, actually. In quantum mechanics, I'm not able to define the position of this particle to better than the Heisenberg uncertainty limit, which means that this particle state is not represented by this infinitely sharp point, but by some fuzzy ball. And that fuzzy ball in quantum mechanics has a limit on its area. And that's actually exactly the Heisenberg uncertainty principle. And so, if I want to measure the position of the particle, then it seems that the fact that the Heisenberg uncertainty principle places some limit on this means that quantum sensing will fundamentally always be worse than sensing in the classical limit. There's no way to do better than classical sensing because there's no limit on how accurately you can sense. And that's different in quantum mechanics. So, you would say that actually quantum sensing only just makes things worse. And that's, as far as I believe, actually, that's completely true. But actually, there is some very interesting stuff that happens when you try to sense down at this quantum limit. And I want to give a little bit of an example of this to give you a flavor for what I mean. So, this is a typical system that we study in my lab. Well, not this physically, but this is the type of system we study. It's called Optomechanics, where the position of a mirror changes the frequency of a cavity. Here, it changes the interference pattern of light between these two mirrors. And what I want to talk about here is using light, laser light, actually, just normal, regular laser light as a quantum sensor. And so what happens, of course, if I want to measure the position of this mass, I can shine a laser and look at the interference of light, and that will tell me about the position of mass. And actually, as you may know, lasers have shot noise. So as I increase the intensity of my laser, actually the precision with which I can measure that the position of that mass actually gets more and more accurate. So this is sort of the start of something I'm going to call what is called the standard quantum limit. And this shows you this exactly what I was just saying. Intuitively, the detected noise, as I turn up my measurement strength or laser power in this case, he goes down. Now, what's interesting in quantum mechanics is that actually, if I turn up my laser power, there's a second thing that happens. And that is that actually my mass starts to experience a fluctuating force, which starts to kick it around. And this is actually something called quantum back action noise. It's and what happens is that if I try to turn up my laser higher and higher, then actually the back action noise starts to shake my mass. And so the noise on the position of my mass actually goes up as I start to measure stronger. And what's amazing, what's really interesting is if you analyze this, these two lines cross at this point here, and this is exactly the point when the detector noise would be able to resolve the quantum fluctuations of that mass. So this is what we call, if you add these two together, which is what you see in your measurement, then actually you have this little curve which goes down. You can never measure the 0-point fluctuations because your measurement always adds exactly an equal amount of noise. And then as you turn up your laser higher and higher, then actually your mass starts to get jiggled around from your quantum measurement. And it looks actually like heating. And sometimes lots of people call this heating, radiation shot noise heating, but it's actually only heating if you don't measure what comes out. And actually, this noise that you see over here is not thermal noise, it's not heat, it's actually quantum noise. And if you record the entire measurement record and take advantage of the quantum correlations that are in there, you can actually completely undo that noise. And that's something that was done a couple of years ago by my colleague in Copenhagen. Good. So that's a little bit about quantum sensing. What's also kind of funny to note is that this doesn't involve, this involves light that is not quantized in the sense of having a discrete energy spectrum or using quantum interference. But I would say that this is actually a extremely good example of really the quantum limit of sensing. So I want to tell a little bit, highlight a few examples of quantum sensing we used to do in my group, and now I'll use the slightly broader term of sensing with quantum objects. The first is this work done by my PhD student Mario Gély, where we've looked at using qubits to sense radio frequency photons. And what's the idea? So the idea is that we have a qubit, which is like a gigahertz atom, and we want to couple that to megahertz photons. And people do this all the time with gigahertz atoms and gigahertz photons. That's the basis of a quantum computer. But now we want to try to push this down an order of magnitude in frequency down to megahertz. And you might ask, why would you want to do that? And the reasons, we have a couple of reasons why this is interesting. First, our mechanical objects often live down in this megahertz regime. Second of all, there's actually spin ensembles that have extremely high coherence times down in this megahertz regime. And finally, from a more fundamental perspective, down in this megahertz regime, there's actually real thermal photons in our circuit. And so you can start to look at trying to do quantum thermodynamics. So the way we did this is a funny, it's a totally weird looking circuit. It's basically an inductor, a capacitor, and a Josephson junction in series. But through the insight we've gained from earlier work, together with Sal, actually, who's in the call today, we understood how to engineer this into 170 megahertz photons, 5.9 gigahertz qubit with ultra strong coupling. And if we look at that, actually, we could see in the frequency spectrum of the qubit, we were able to directly observe the quantization of the photons at 170 megahertz in our circuit. So that was one highlight. Another highlight of what we've been doing lately is what I'll call quantum sensing with SQUIDS. And the basic idea, one of the things we've done with this is actually using SQUIDS to try to sense the displacements of this little beam. So this is a suspended beam of 20 nanometer thick aluminum, a few microns long, and the idea is that somehow we want to use the flux that is inside of this superconducting loop to sense the displacements of this beam if it bounces up and down. So how do we do that? The first is a little bit of a tutorial on how SQUIDS work. So SQUIDS are a device that takes a supercurrent, it splits it in two, and with these junctions in between. And if I look at, if I put a magnetic flux here, I get an interference of these two supercurrents when they recombine. And that means that the critical current of this object oscillates up and down with a periodicity given by the flux quantum. So one of the nice things about SQUIDS is they're super sensitive objects. So one flux quantum is a super small number. So for a relatively small loop of 10 by 10 microns, that's 20 microtesla already. And for that reason, people do crazy things like hang SQUIDS off of helicopters to sense oil under the ground, and use SQUIDS in hospitals, or at least medical experiments, to try to sense the magnetic currents from thoughts in your brain. So that's the bit of background about SQUIDS. And what are we going to do with SQUIDS? We're going to work in microwave frequencies. So there's one important concept that I need to introduce as well, which is that if I take a Josephson junction, which is one of the junctions in the SQUID, and I put it in series with a capacitor, it turns out this Josephson junction looks like an inductor. So this looks like an inductor capacitor circuit, and that's how we make things that resonate at microwave frequencies. We just pick a capacitor and inductor to make this frequency microwave frequencies. And the last ingredient, if you combine these two together, then if I have a SQUID in parallel with a capacitor, then this is something where I can tune the frequency of my cavity by changing the magnetic flux. Now, the whole idea is that if I have this very high Q cavity, because I have a good superconducting cavity, and I reach this point of this very high slope, that allows me to use the frequency of the cavity to do extremely sensitive measurements of flux. And that is what we are going to apply to try to do sensing with these devices down to the quantum level. So how do we do that for position? Actually, to do this position, we make part of our SQUID loop bounce up and down, and then we put a magnetic field parallel to this. And actually, because this goes up and down, it changes the magnetic flux that's enclosed inside of the SQUID loop. And that is a way that we can translate positions, vibrations into magnetic flux. So that's what we've done recently. So this shows a picture of the device. This is our little SQUID. We have a huge capacitor here, and this is a transmission line we'll use to read it out. Using this, we are able to detect, we are able to see the mechanical resonance here. It turned out it had a very high quality factor, which is always good for our type of experiments. We were able to see the thermal noise of these vibrations, even at 15 millikelvin. So at cryogenic temperatures, there's still some Brownian motion of these devices, and that is something that we are able to sense using this device. And we were able to confirm that that this coupling rate and sensitivity scales linearly with the magnetic field, and hence the magnetic flux in that loop, enclosed by the thing bouncing up and down. So the next thing we've done with this is actually make something what I'll call a quantum galvanometer. And there the idea is that now instead of sensing position, we're going to try to sense quantum fluctuations of current. And there the idea is over here. Now, instead of putting having the flux being in this SQUID device, the same device more or less here, but instead of having that the flux in this loop being modified by the position of a beam, we're going to connect this this loop with a mutual inductance to a wire that has a current flowing in it. And the idea is that if there's current flowing this wire via the mutual inductance, it will induce flux in the SQUID, and then that will tune a little bit the frequency of our cavity. And our aim will then be to actually sense the 0-point fluctuations of the current going back and forth in this wire using the frequency of this SQUID cavity. So that is something that we did recently, and this was generation 1, just recently published in Nature Physics, and generation 2 we've optimized already, and we're already getting things ready. But actually, it turns out with generation 2, we were also able to take the thermal fluctuations of that current and cool that low frequency circuit all the way to its quantum ground state using the high frequency circuit. So actually these devices work two ways. We can not only sense with them, but we can also manipulate the state of the thing that we're sensing. That actually always comes one in hand with the other when you work in this quantum sensing limit. So, and then a last topic, and this is sensing with massive objects. If you want to learn more about the ideas of this, I was recently part of a panel in the UK on Zoom, and you can find a link on YouTube. And here the idea is that if we can somehow engineer quantum superpositions of masses, then in principle we have created quantum superpositions of gravitational fields, and that means quantum superpositions of space-time. And that is something that that people do not understand how to even write down the equations of, conceptually even. And so in this panel, we actually go into quite some detailed discussion about what would be needed in these experiments, in these types of experiments, and what are the routes to pursue. So the platform that we work on is this guy here. This is a 350 micron membrane like the one I showed earlier, but now we've built it into this phononic shield to prevent phonons from leaking out, to give it a very high quality factor. And we're currently working on experiments where we want to cool this membrane to its ground state and then start to look at making quantum superpositions of its motion, which means that we would in principle have quantum superpositions of space-time. Now, I will, in the last few minutes, I guess, of my talk, I want to change gears and talk about a different topic that we've been working on in the group, and that's in this topic of quantum simulation. So what is quantum simulation? This is the idea, this is an idea that came out a little bit out of Richard Feynman. You know, these problems there are problems in quantum physics that are extremely difficult to solve. Some examples, for example, there are problems in quantum chemistry which are basically computationally impossible on even supercomputers, and there are outstanding problems in physics that people just do not understand. And one is, for example, high temperature superconductivity and strongly correlated electron systems. So in general, the approach, the problem is that we have some Hamiltonian, typically a many-body Hamiltonian, that we do not have an answer for, and we want to solve it. And on the other side, you have some hardware. You know, for me, this is always an inductor and a capacitor in some sort of combination on a chip. And now there are two routes to using this hardware to solve this problem. There's sort of what I'll call digital simulation. So you can make an approximation of this hardware as a qubit, and that's what people do with transmons. And you can do a lot of work to make sure that this qubit, this device here, acts like a qubit, and then you know, you'll have a qubit that you can do digital simulations with, and then you also need to encode this Hamiltonian into gates of that qubit, or actually multiple qubits. And if you combine all these together, you'll get what I'll call a digital quantum simulation. And there's an alternative route is actually what I'll call analog quantum simulation, and that's something that I find that I find quite interesting myself. And that's the idea of trying to play with the hardware and map the hardware as accurately as you can onto the Hamiltonian you're interested in, and actually build the Hamiltonian in hardware. So I'll show an example of this, of a type of quantum simulation, if you want, that we've done. And this is actually a funny qubit. This guy here that Sal made actually when he's a PhD student in the group. And yeah, we made this for different purposes, but it turns out this had a very interesting property when we built this device. And that is that actually this device reached what's called the ultra-strong coupling regime, where we had a gargantuan vacuum Rabi splitting between the qubit and the photons in the resonator. And that's pretty cool. I mean, we get a really big number. And also we could show that this was something that went beyond the rotating wave approximation, which means that this is ultra-strong coupling regime where counter-rotating terms play a role in your Hamiltonian. But actually what was more interesting for me that came out of this is when we tried to understand this data quantitatively, we ran into some problems. And then actually, in particular, my student Mario and my postdoc Daniel came up with a very interesting solution. And that actually, that solution motivated by experiments, actually, I believe has a much broader application than just understanding our data. And I think, this is an example, at least, of where we've shown that renormalization, a problem that is a broader problem of quantum electrodynamics, can actually arise naturally on its own if you do the circuit analysis properly. And we're still interested in seeing how that maps to other systems. A spin-off of this work actually was also a software package called QuCAT. Through the way we learn to understand these circuits, we came up with there's a sort of way to analyze these circuits in a systematic way, but this is all done by hand, and Mario was very dedicated to automating that, and that is what he's done with the software package here, where you can basically draw whatever you want in a circuit, push a button, and it will give you all of the spectrum of that circuit and output a Hamiltonian to whatever order of perturbation you want for calculations. And the last topic I'll talk about quickly before I summarize is recent extension of this work. So this work, we were looking actually together with a PhD student, Marius, who had worked earlier with in Leo De Carlo's group. We looked at building nodes of qubits that are where the coupling between them, not only the sign, but also the nature of the coupling between them can be tuned with a static magnetic flux. And more recently, there's been predictions from theorists that actually, if you replace that static flux with a dynamic flux, an oscillating flux, you can engineer interesting things like Kitaev honeycomb models and arbitrary spin-spin interactions using these transmon qubits. And that's something that we've been working on recently, and hopefully we'll get some exciting new results when the devices get out of the clean room. So as a summary of what I told you about today, I told you about quantum sensing, and where in my group we've pushed, we've used engineering to push sensing to the quantum limit. That's for me really what quantum sensing is. If you can reach the quantum limit, that is quantum sensing. And the applications we have there are looking at things like force sensing, transduction, to microwave optical transduction, for example, which is also something that Simon Groblacher in our department works on extensively, but also looking at things like trying to sense the possible superposition of space-time using the very heavy devices we can make. And then the other thing I told you about today is these quantum simulations, where for me, the most exciting thing about quantum simulation is getting insight into the physics by building the circuits and doing the experiments with applications in chemistry, many-body theory, and just understanding physics. So, and of course, I don't do all the work at all. Sometimes in the lab, not so often anymore. But of course, the real hard work is done by the great people that work in the team. And this is a photo from a few years ago with still many people in the group these are the people, of course, that do all the real work. So with that, I would like to thank you for your attention, and